Welcome to the lesson on movement systems. By the end of this lesson, learners will be able to define the movement system of a robot and name the three types of mechanical movements. Learners will also be able to explain the degrees of freedom of a robot and how this enables it to move in different ways and carry out the necessary tasks. A movement system or mechanical motion is essentially a combination of mechanical parts that work together to accomplish a specific task. In the practical case of a robot, this translates to a series of linkages and motors. The way these motors rotate and are positioned determines the robot's motion, enabling it to reach different points. These mechanical components constitute the robot and form the manipulator itself. Three primary motions are observed. These are rotational motion, linear motion, and reciprocating motion. Rotational motion occurs when the end effector moves in a circular path around a fixed point or axis. Linear motion involves the movement of the end effector in a straight-line path from one point to another, and reciprocating motion, which involves back and forth movement of the robot arm or end effector along the same path between 2 points. Some examples of robotic arm motions in EV manufacturing are listed here. Examples of rotary motion include screw-driving robots for battery pack assembly and wire harness winding robots for cable routing. Linear motion is demonstrated by battery module placement robots and paint application robots that move along the vehicle body. Reciprocating motion can be seen in spot welding robots for body panels and vision inspection robots that perform quality control. Degrees of freedom, abbreviated as DOF, refers to the number of independent movements or variables in a system that define its state or configuration. It represents the number of parameters that can change independently without violating the constraints of the system. In mechanical systems, DOF represents the number of independent ways an object can move in 3D space. To fully understand how mechanical components function, move, and constrain the robot's movement in space, we must first define DOF. This image illustrates the general DOF for any linkage or body in space. There are three linear or translational DOF, which can be visualized as movement left and right, up and down, and forward and backward. These correspond to the Cartesian coordinates x, y, and z. In addition to these, the image highlights three rotational DOF represented by the green, orange, and light blue half circles. These correspond to rotations around each of the axes x, y, and z, resulting in movements like roll, pitch, and yaw, which determine the body's orientation in space. A free body typically possesses 6 DOF, 3 translational and 3 rotational. A robot can have multiple DOF. For example, it might have independent DOF for movement in the X, Y, and Z directions. However, it may also have additional joints that move in the X direction but are rotated or translated differently, resulting in more than 6 DOF. While a robot may have multiple degrees of freedom, the most crucial information typically relates to both the X, Y, Z position and orientation of its end effector in space. The number of controllable DOF varies among robots. For example, a robot with only 3 joints that control X, Y, and Z position would have limited ability to control the end effector's orientation. A minimum of 6 DOF, 3 for position and 3 for orientation, is needed for full control of the end effector in 3D space. Understanding DOF is essential for analyzing and designing robotic systems, as it determines the robot's workspace and ability to perform required tasks while operating within its mechanical constraints. Degrees of freedom are important because they determine a robot's ability to perform high-precision tasks, such as inserting and connecting battery cells and positioning electric motors in EV manufacturing. Robots typically utilize 6 DOF to achieve proper orientation and alignment when handling EV components, as this allows complete control of both position and orientation in 3D space. Precise handling is critical in EV assembly since even minor misalignments during component installation can significantly affect the vehicle's overall performance.
What is 6 degrees of freedom, or 6 DOF for short? 6 DOF refers to the freedom of movement of a rigid body in 3-dimensional space. But anyone can Google 6 DOF and get that definition. What does it actually mean? Put simply, the degrees of freedom refer to the ways our bodies and other objects can move through the space around us. Take the space shuttle, for example. It can move along 3 axes that are commonly referred to as the Cartesian, or X, Y, and Z plane, which you might remember from algebra class. It can move forward or backward on the X-axis, left and right on the Y-axis, and up and down on the z-axis. There are, however, 3 more movements the shuttle can make. The shuttle can roll on the x-axis, it can pitch forward or backward on the y-axis, and it can rotate or yaw in a circle on the z-axis. Those are the 6 basic movements, or degrees of freedom, that any object can make. But not every object can move in all 6 degrees. Fingers, for example, can't move independently of the hand in the x, y, and z planes, but they do have pitch, roll, and yaw capabilities. So if there are only 6 degrees of freedom, how can we see robots that have 20 or more degrees of freedom? Each moving part or joint on the robot has up to 6 DOF. Returning to fingers, each one has 3 degrees of freedom, as do wrists, elbows, and shoulders. Our hips, knees, ankles, toes, necks, even ears have their own degrees of freedom, and they all add up. And in manufacturing, each joint and the 6 potential degrees of freedom that come with it represents a value that must be captured and tracked to ensure accuracy. This makes having a laser tracker that can capture all 6 DOF for the probe or sensor measuring a part essential in today's automated manufacturing environments.
After understanding DOF, we can see how a part can move in different ways, translating along and rotating around the X, Y, and Z axes. When we consider the actual physical components of the robot and where these motions occur, we can effectively design and build the movement system. 3 key parts influence a robot's movement and functionality: manipulators, motors, and shafts. Manipulators are the physical components of the robot arm, marked number 1 in the image. These are solid linkages that connect different joints, and their configuration ensures both reach and dexterity in manufacturing spaces. Motors, marked number 2, are the actuators that serve as power sources. Motors drive the movement between linkages. For example, a robot with 3 motors can provide 3 DOF. The orientation of a motor determines how 2 linkages move relative to each other. While revolute joints create rotary motion, prismatic joints create linear motion. These motors provide controlled torque for precise operations like battery assembly or cable routing. Shafts, marked number 3 in the image, are power transmission elements that connect the motors to the linkages. For instance, a base shaft changes the robot's orientation relative to the ground. The combination of these 3 components determines the robot's movement capabilities when individual or multiple joints are activated. In summary, robots require a movement system to perform their designated tasks effectively. While robots previously had limited capabilities with only 2 degrees of motion, left, right, or forward, backward, modern industrial robots now typically utilize 6 degrees of freedom that allow 6 distinct degrees of motion. These movements are achieved through 3 common types of mechanical motions: rotary, linear, and reciprocating, enabling robots to perform complex tasks with high precision. Thank you.